A deadlock is a situation that occurs in a system when two or more processes are waiting indefinitely for resources held by each other, and as a result, none of the processes can proceed. In simple terms, it's a condition where every process in a group is waiting for an event that can only be caused by another process in the same group, causing all of them to remain stuck forever. Real-life example: two cars on a narrow road. Imagine a narrow one-way road where only one car can pass at a time. Car A enters from one end, and car B enters from the opposite end. Both meet in the middle and stop. Car A cannot move forward because car B is blocking the way. Car B cannot move forward because car A is blocking the way. Neither car can move unless the other backs up, but both are waiting for the other to do it. So, both cars remain stuck forever. This is exactly what happens in a deadlock. Computer example. Process 1 holds resource A and waits for resource B. Process 2 holds resource B and waits for resource A. Neither process can continue, leading to a deadlock. Characteristics of deadlock. Deadlock is a situation in which two or more processes are blocked indefinitely, waiting for each other to release resources that they need. For a deadlock to occur, four necessary conditions, known as the Kaufman conditions, must hold simultaneously. Mutual exclusion. At least one resource must be held in a non-shareable mode. That is, only one process at a time can use the resource. If another process requests that resource, the requesting process must be delayed until the resource has been released. Example. A printer can only be used by one process at a time. Hold and wait. A process must be holding at least one resource and waiting to acquire additional resources that are currently being held by other processes. Example. Process A holds resource R1 and is waiting for resource R2, which is held by process B. No preemption. Resources cannot be forcibly taken away from a process. A resource can be released only voluntarily by the process holding it after that process has completed its task. An example. If process A holds a printer, the operating system cannot forcibly take the printer away from process A and give it to process B. Circular wait. A set per P1 of waiting processes must exist such that P0 is waiting for a resource held by P1, P1 is waiting for a resource held by P2, Pn1 is waiting for a resource held by Pn, and Pn is waiting for a resource held by P0. Example. Process A is waiting for a resource held by process B, and process B is waiting for a resource held by process A, creating a circular dependency. If all four of these conditions are met, a deadlock can occur. However, the presence of these conditions does not guarantee that a deadlock will occur, but it makes it possible. Real-world examples of deadlock. Deadlocks are not limited to computer systems. They can occur in various real-world scenarios. Understanding these examples can help to better grasp the concept of deadlock. Traffic intersection. Ski scenario. Imagine two cars approaching an intersection from perpendicular directions. Each car enters the intersection intending to turn left, but they both stop in the middle of the intersection, blocking each other's path. Neither car can proceed until the other car moves. Deadlock conditions. Mutual exclusion. The space in the intersection can only be occupied by one car at a time. Hold and wait. Each car is holding its position in the intersection and waiting for the other car to clear the path. No preemption. Neither car can force the other to move. Uncircular wait. Car A is waiting for car B to move, and car B is waiting for car A to move. Dining philosopher's problem. Sound scenario. 5 philosophers are sitting around a circular table. Each philosopher needs 2 forks to eat. There is 1 fork between each pair of philosophers. Each philosopher picks up the fork to their left and then tries to pick up the fork to their right. If all philosophers pick up their left fork simultaneously, they will all be waiting for the fork to their right, which is held by their neighbor. And deadlock conditions. Mutual exclusion. Each fork can only be held by 1 philosopher at a time. Hold and wait. Each philosopher is holding 1 fork and waiting for another. Stunt. No preemption. A philosopher cannot take a fork from another philosopher. Circular wait. Philosopher 1 is waiting for philosopher 2, philosopher 2 is waiting for philosopher 3, and so on, until philosopher 5 is waiting for philosopher 1. Resource allocation in manufacturing. Scenario. 2 machines, A and B, are required to manufacture 2 products, X and Y. To manufacture product X, machine A needs to process the raw material first, followed by machine B. To manufacture product Y, machine B needs to process the raw material first, followed by machine A. If machine A starts processing raw material for product X and machine B starts processing raw material for product Y simultaneously, and each machine then needs the other machine to complete its process, a deadlock occurs. As deadlock conditions. Mutual exclusion. Each machine can only process 1 product at a time.